Welcome back to ECE 442-542. Let's now wrap up this video in lecture 7.3 with the fourth part, and this is now the general controller design. What we want to look at now is if we now have the ability to locate poles and zeros in the complex z-plane, how can we do that if we're forced with controlling an unstable system or maybe controlling a non-minimum phase system? And a non-minimum phase system is a system that possesses finite zeros outside the unit circle. And this design strategy is all based on our understanding of, or our insight into, root locus. So suppose somebody provides us with the following transfer function, g sub 2 of z. It's now unstable. We have a 0 at 1, and we have another pole at 1/2. So now somebody says, well, can you stabilize that system with a controller c of z? If we let c of z be a constant gain controller, what's going to happen? What's the root locus? Now we invoke rule 2, I believe, which is now which of these line segments belong to the root locus. This line segment, so that pole will migrate to that 0 at 1. The line segment between 1/2 and 1 is not belonging to our root locus because there's an even number of poles and zeros to our right. And we now have this real axis segment on our root locus. And now what happens? As we increase the gain k from 0 to infinity, we are always stuck between z equal 2 and z equal 1. That's outside the unit circle. And so we never get inside the unit circle. And with a pure gain controller, that's what I'm meaning by a pure gain. We just have a gain k. As long as we're restricted of having that k between 0 and infinity, we're not going to be able to stabilize the closed loop system. So what do? We can't use just a pure gain controller. Here is our system. We have a 0 at 1, an unstable pole at 2, and we know what's going to happen if we just used a gain in our controller. So now what do? Well, we are trying to eliminate always being stuck between between 1 and 2. And how can we make that happen? Well, one way we can eventually get off of that segment is to in fact introduce an unstable pole in our controller, and because we're, I hope at this point, very comfortable sketching a root locus where we have 2 poles to the right of a 0, what if we canceled that? We can always cancel poles or zeros inside the unit circle. So now I've canceled a canceled a pole in our plant at 1/2 with this 0 factor, z minus 1/2 in our controller. And I've introduced an unstable pole factor in our controller. Again, I'm sort of going back to 2 bads may actually make a good. And what's the root locus of this look like? Now you can effectively forget that pole 0 cancellation in thinking about sketching this root locus diagram. That is no longer there. We now just look at what segments on the real line belong to our root locus, and we look for those segments that possess an odd number of poles and zeros to our right. We will have a segment between 3/2 and 2. We will have another line segment belonging to the root locus to the left of that 0 at 1. And I think you can now sketch this you know that this is 2 poles to the right of a 0. We have a circle centered at, and this isn't the right way to do this necessarily, but if you, well, let me just do it. We know that this is a circle, so just assume that you believe that that's a circle. One goes here and the other one goes there, and what's the radius of this circle? The radius of that circle, r, is the geometric mean of the distance of that 0 to the first pole, which is 1/2, and the distance from the 0 at 1 to the pole at 2, which is 1. So this is now the square root of, the numerator is 1, and we have the square root of 2 downstairs, or we can now say that that's the square root of 2 over 2 for our radius. Now, the reason I said I wasn't drawing it right is because this now actually needs to be to the left of 1/2 by this 0.2 amount. So let's say that it comes in there. This now needs to be to the right of, or be breaking away at 0.7 away from 1. So let's say that's right here. And this now needs to come in there. But I hope you can see that as long as we crank up the gain to that particular point, and we know that that point is r away from that 0, we know that this distance is 1, and we know this length from 0 to the, from the origin to the 0 is 1. That's now an isosceles triangle, and we can calculate the angle, and we can actually calculate what this point is where we first enter the unit circle. That's what I'm calling z sub square. And we will then find that we can crank up the gain a little bit more and maybe say, oh, let's make our closed loop poles such that they are at the cloud locations. Well, here is some of the analysis that we could now perform. We have a controller that has a 0 at 1/2, which cancels the pole at 1/2. We can always cancel poles and zeros inside the unit circle. We have a pole at 3/2 from our controller. We have an unstable pole of our system at 2, and we have that 0 right on the unit circle at 1. We can now compute the gain, or create the gain formula from our gain condition. We now know that k sub square is determined by this product of pole factors divided by the 0 factor at z square. And again, you can determine where that z squared is based on having a triangle with 2 equal sides. We have a side of 1 there and a side of 1 there. We know the base is of length r. We can now use our law of cosines to find out that angle, acute angle at the origin, and that now gives us our poles at z square. And if we calculate the gain at that z square, we end up with the gain to get us stable being at 2. We just keep going, and eventually we see that if we crank up the gain enough to get us to the star, then we will start to become unstable, and that's just now computing the gain at z equal to -1. That's an easier computation, and that's now 3.75. We now know that if we used this controller, which is unstable, with this unstable plant, we will actually produce a stable closed-loop system as long as our gain on that controller lives between 2 and 3 3/4. Is there another way to stabilize that? And yes, there is. There's all sorts of ways to stabilize this system. This is still the same plant. Now you could actually say, oh, why don't I just put the pole right there at 2 and again cancel that particular 0 or the pole at 1/2. Now my controller is k z minus 1/2 over z minus 2. And you know what this root locus looks like, because the geometric mean now, with L1 equaling 1, L2 equaling 1, and the square root of 1 is 1. Now if I could draw this, this would now have a radius of 1. That's supposed to be a circle. 1 goes towards that finite 0. The other one zips off to minus infinity. But now you can see that as long as our gain is big enough to get us beyond that square location on the root locus and stay to the left of star, we will remain stable. And that's another stabilizing controller, but it is an unstable controller combined with an unstable plant to produce a stable closed loop system, as long as k is between k star and k rectangle. What about this system? This system now is non-minimum phase because we have a 0 outside the unit circle. We have a pole right on the stability boundary, right at z equal to 1, and we have another pole at the origin. What happens if we actually used a pure gain controller k? Now we cut our French bread. We say, oh, which line segments belong to the root locus? And we see that we have that, and there's no way with a pure gain controller that we can stabilize this, because the pole at z equal to 1 just remains outside the unit circle for all values of k. With a constant controller, we can't stabilize this non-minimum phase system. Can we stabilize this system? What would be a way to stabilize this system? Well, the last time we found that, oh, if we put an unstable controller in, that helped. But in this case, we now are stuck between wherever that pole is and that 0. So that's not going to work. But that was now for this is now a 0 outside the unit circle. What would happen if we now put a 0 there? Now we have just that piece of our real axis eventually on the root locus. We can't get away with a improper transfer function, meaning we have to make this at least proper. We have to introduce another pole. If we now put in a pole, let's say at 1/2, what's the root locus now? Now we know that we have that segment and we have this segment. So that we start at the poles. These two actually break away and will leave and go into or outside the stability region and eventually approach those finite zeros. And this now says that as long as we crank up the gain only enough to get us to that box, we will remain stable as long as that box hopefully has the third pole inside the unit circle. Now our stability, let's just say that that's the case. then our range of k for closed loop stability would be for k being between 0 and k box. Now we are stable as long as k is equal to 0, bigger than 0 and less than k box, as long as this box stays to the stays to the right of -1. If it would be that, oh, in fact, we needed to crank up the gain only to get us to those triangle locations, or let me say it another way, maybe when we cranked up the gain and found that the triangle went outside the unit circle, these aren't consistent, so I'm not going to leave those in there together. But I hope you see that you need to check two different locations. You need to check the box location and the gain at -1, and hopefully the gain to get you to -1 is larger than the gain to get you to the box. If it's not, then you may be becoming unstable when you pass through the unit circle at -1 before you pass out of the unit circle on the right, going towards those finite zeros. But in general, I would expect your stability to be bounded by the root locus branches exiting the unit circle from those two poles to the right. That now, I hope, gives you a little bit of intuition into how you might stabilize with generic controllers, with general controllers. Here we now had a non-minimum phase controller. It was stable, but we needed that in order to stabilize this non-minimum phase system. We also before had to introduce unstable controllers to stabilize an unstable plant. That will hopefully get you some intuition into how to design general controllers for unstable systems and non-minimum phase systems.